Okay, so what we are going to do today is chapter 5. Chapter 5, the first thing that I want to talk about is finding areas of certain types of regions. We already learned in chapter 4 how to find the area below the graph of a non-negative function above an interval from a to b, right? So the area below the graph of a non-negative function f above the interval from a to b is given by the integral of f of x from a to b, right? You guys remember that? So we learned that in chapter 4. That was one of the motivational examples that I gave you when we talked about a definite integral. Now, today we want to learn how to find areas of more general regions. So this is the region that I want to look at today. I hope you didn't see that. Let's say I have the yellow region, and let me explain what that region is. That region is bounded above by the magenta graph, which is the graph of the function y2 of x, and the yellow region is bounded below by the green curve. That's the graph of y1 of x. On the left hand side, the region is bounded by the vertical line at A. On the right hand side, the region is bounded by the vertical line at B. So this region is bounded above by the graph of a function, bounded below by the graph of another function of x. On the left, it is bounded by a vertical line. On the right, it is bounded by a vertical line. So that's the region, and we want to know what's the area of that region. Is this clear? Everybody sees what the region is. Okay, what is this area? Do you have any idea of how I can compute this area? Say it again. Well, did you look at what I wrote before, or did you just know that answer? Okay. Okay, he just killed my enthusiasm for All right, so what I want to show you is that how to come up with the area by using what we learned in chapter 4, okay? So this region is not a region like the one that we saw in chapter 4, like this one, right? But how can we use that to come up with the area formula for this general region? Well, the idea is, what I want to do is I want to add a large positive constant. So there might be some parts of the region that is below the x-axis, right? Some parts of the region may be below the x-axis. What I want to do is I want to translate the region above the x-axis. Okay? How would I do that? Well, I'm going to add a large constant, positive constant, to the function y2 and the function y1, so that the graph of y2 plus c and y1 plus c goes above the x-axis. So here's what I'm going to do. I am going to add a large constant c to both y2 and y1, so that the graph of y1 and y2 goes above the x-axis. Okay? So I'm basically translating the graph of y1 and y2. If I translate it upward, so basically what this is doing, when I add c to both y1 and y2, it is translating the yellow region upward. It is translating the yellow region upward. You realize that? Now it is did the area change? No, I still have the same area, right? Because all I did is I translated, I shifted the region upward by C units. I did that so that my region goes above the x-axis. Now it's clear what the area A is. Why? Because from chapter 4 we know what is the area below the magenta curve, right? The area below the magenta curve above the interval from A to B is what? So I'm looking at the area below y2 plus c above the interval from A to B. What is that? Well, that's the integral from A to B, y2 of x plus c, right? That's what we learned from chapter 4. And what is the area below y1? What is the area below y1 above the interval from A to B? Well, that area is also the integral from A to B of y1 plus c, right? So now I can find the area of the yellow region by using the concept from chapter 4. Now, these two integrals, they have the same limits of integration. I can put them into one. So these two integrals can be written as the integral from A to B of y2 plus c minus y1 plus c. And when I take the difference, c cancels out, and I am left with just the integral from A to B of y2 of x minus y1 of x. Notice c vanished, right? C doesn't play a role, which it shouldn't have, right? All we did is shifted the region, so the area should not depend on c. So the area is given by y2 minus integral of y2 minus y1. So now I can go back to this picture here. I wanted to know what's the area A, which is bounded above by a function, bounded below by a function of x, bounded on the left by a vertical line, bounded on the right by a vertical line. And that area, we found out, is that all it is that it is the integral from A to B of y2 minus y1. And this is it. That's the area of such a region. Okay. Did that make sense? Okay. Now sometimes there are regions where the region is not bounded by functions of x, but you can view the region as bounded by functions of y. Okay. Let me show you a graph. Let's now consider this region. Again, the yellow region here is what? Now it's bounded above by a horizontal line at B, bounded below by the horizontal line at C, bounded on the right by the function x2 of y. Now, the green curve, that's not a function of x, right? The green curve is not a function of x. However, view it this way, it's a function of y. I can view x as a function of y. Realize that? So think about switching the roles of x and y, basically. So I can think of the green curve as a function of. I can think of the green curve representing x as a function of y. You okay with that? And the magenta curve is the graph of a function x1 of y. So it is defining x as a function of y as well. So on the right side it is bounded by a function of y. On the left side it is bounded by a function of y. What's the area here? The same concept. The area is, now you go from integral from c to d. Which one, as functions of y, which one is bigger, x2 or x1? As functions of y, x2 is bigger, right? Because, given any y value, what's the x2 value? The x2 value is this, and x1 value is this, right? You realize that? So, in this case, the area is given by the integral from c to d of x2 minus x1. Okay? What's the difference between the two regions? It's important that you realize the difference between the two types of regions. I'm going to call this type 2. And I am going to call the other one type 1. Okay? In type 1 case, notice the yellow region is basically the yellow region, you can think of that as the collection of vertical line segments, right? So this region, I can think of it as from A to B, I can think of it as vertical line segments, right? It consists of vertical line segments from A to B. Am I making sense? And the other region, from C to D, I can think of this as consisting of horizontal line segments. Right? You see that? That's type 2. And we know exactly how the area is calculated. Well, what's next? Well, the next thing to do is go over some examples, okay? Did you guys need some time to draw any of these pictures? Alright, so my first example. Find the area of the region bounded by the graph of the equation y equals to x squared plus 1, y equals to x, x equals to 0, and x equals to 1. So there are 4 equations here, and we want to look at the region bounded by all four curves, and we want to find the area of that region. What do I have to do? Do I know whether I should I view this as type 1 region or type 2 region? Well, before I decide that, I have to look at it, look at the graph, okay? All right, so what is the graph of x equals to 1? It's a vertical line and 1. X equals to 2, which is the y-axis. Y equals to x, straight line, the black straight line. Y equals to x squared plus 1. That's the parabola. Where is the vertex? Without the 1, the vertex is at 0. With the 1, shift upward. Vertex is at 1, right? So I didn't draw I didn't draw half of the parabola, right? Because the reason I didn't draw the left half of the parabola is because also I didn't draw the left half of the line y equals to x, because the region is bounded on the left side by the y-axis. So it is bounded on the left side by the y-axis, bounded on the right side by x equals to 1, bounded below by y equals to x, bounded above by y equals to x squared plus 1. What type of region is this? Is it type 1 or type 2? Remember, type 1 means it's between two graphs of functions of x. Type 2 means it is between the graphs of two functions of y, right? This is type 1. This is type 1. Okay, what's the area? What's the area A? What is this area? Note the region extends from where to where? The region extends from 0 to 1, right? Extends from 0 to 1, and you can think of the region between 0 and 1. It consists of vertical line segments. And the integral will go from 0 to 1 of what? The function above the upper bound minus the lower bound. Upper bound is x squared plus 1, very good. And the lower bound is x, and I take the integral here. Is that a easy integral to compute? Yeah, it's just powers of x, right? We know how to use the power rule, come up with the antiderivative, evaluate it at 1 and 0, subtract, right? However, I'm not going to do that to save some time. But I have a little cheat sheet here. You might not see it. Intentionally, I did that. I wrote 5/6 in the yellow right here. I wrote 5/6 right there. I'm trying to cheat, okay? So the final answer is 5/6. I wrote 5, 6 there so that you cannot see it, but I will remember the answer, right? Okay. Okay, the answer is 5, 6. Okay, right here, right by A. Right next to the A. Right by A. Okay. All right, so that's the answer. I'm confident that you can go over the integral and come up with the answer. But I also didn't do this intentionally because in your exam, I am going to ask you to set up the integral to find the area. So I'm going to say, in this problem, I'm going to say, set up an integral to find the area of the region bounded by blah, blah, blah. Okay? And so what it means is that your answer is right here. Your answer is right here. Okay? You don't have to give me the numerical answer. Why? Because I'm going to be asking you integration problems separately anyway, so how many times do I want to test you on finding integrals? Well, not too many times. So in this case, I want you to just set up the integral. And also it makes my grading easier. Okay? All right. So next example. My next example is find the area enclosed by the graph of the equation y equals to x minus 1 and y squared equals to 2x plus 6. Find the area enclosed by the graph of the line y equals to x minus 1 and the graph of the parabola y squared equals to 2x plus 6. Well, once again, before you determine whether it is type 1 or type 2, what would be the limits of integration, you have to draw it, sketch it, see, and then it's going to tell you how to integrate, how to find the area. Well, first of all, the graph of y equals to x minus 1, we all know, right? What's the graph of y equals to x minus 1? It's a straight line, making a 45-degree angle with the positive x-axis, right? What's the graph of y squared equals to 2x plus 6? Here's one thing I'm going to do here is that I'm going to solve for x here. X would be y plus 1. And here I'm going to also solve for x. So what would be x if I it would be half y squared minus 3. Am I right? Okay, what is the graph of x equals to y squared? What is the graph of x equals to y squared? Forget about the half. What's the graph of x equals to y squared? It's a parabola that opens to the right with vertex at 0, 0, right? If I have just x equals to y squared, the graph is a parabola that opens to the right, vertex at 0. Now with the half, it doesn't change the vertex, right? It doesn't change the vertex. It just stretches the curve. And with the negative 3, the vertex, where does the vertex go? It goes to the left by 3 units. So my vertex is at negative 3. So I have the parabola that opens to the right. The vertex is at negative 3. I have the straight line, and the straight line is easy to draw, right? I am confident all of you know how to sketch the graph of a linear equation. But there is one more difficulty here, which is you need to know the intersection of the two curves. Okay? And how do I come up with the intersection of the two curves? I need to know that the intersections precisely. Was that? Very good. So I have x equals to y plus 1 here, x equals to half of y squared minus 3. To come up with the intersection, I have to equate them. And then let's just multiply both sides by 2. And then this becomes y squared minus 2y minus 8 equals to 0 if you simplify. And then can you factor that out? Can you factor that out? What is that? So that's what we get. And then what are the values of y? 4 and negative 2. Then how do I find the corresponding x values? Once I know that y is, so from here I get y is 4 or y is negative 2. When y is 4, I can plug in 4 here and get x to be what? 5. When y is negative 2, I get x to be negative 1. So that's why I have the intersection at negative 1, negative 2, intersection at 5 and 4, right? Everybody is clear? So that completes my picture. Remember the region is bounded by both curves, so the region is the yellow region, right? You agree? Yellow region is the only region bounded by both curves. And I have to find the area of that region. Okay, so how do I find the area of this region? Is it type 1 or type 2? Type 2 because the region extends the y coordinate, right? Extends from negative 2 to 4. And this region consists of, this region is bounded on the left by the graph of a function of y. Well, what is this blue curve? The blue curve is the function x. Is the function x equals to what? Half y squared minus 3, and it is bounded on the right side by the function y plus 1. So this is my x2 of y, right? This is my x2 of y, and this thing here is my x1 of y. So what's the area A then? What is the area A? It is what integral? I can think of this. Remember, type 2 means what? Type 2 means bounded above by the horizontal line at D, bounded below by horizontal line at C, bounded on the left by the graph of x1, bounded on the right by the graph of x2. Here, what's going on? It's bounded above by the horizontal line at 4, bounded here by the horizontal line at negative 2, bounded on the right by x2, bounded on the left by x1, right? You agree with that? The horizontal lines, in this case it's a little bit confusing because the horizontal lines above and below, they are just one point at that intersection, right? So what is the area then? Integral from where to where? Negative 2 to 4. Okay, which function comes first? The function x2 comes first, right? So that would be y plus 1. And then what's the next function? Half y squared minus 3. And then I have to integrate that. And again, I am not going to compute this, and I believe the answer is 18, just because I looked it up before I came. Okay. Everybody's okay? Again, the computation of the integral is not the problem here. The problem here is sketching the curves, recognizing whether it's type 1 or type 2, and forming the correct integral for the area. You agree? It turns out I can also find out the area A by using type 1 regions. However, this is, as a whole, it's not a type 1 region, but I can break it up. I can break it up into two regions, and each region can be then thought of type 1 regions. How? Well, think about -1. If I divide the region right at -1, then the right hand side is a type 1 region because it is bounded above by a function of x, bounded below by a function of x, right? On the left by a vertical line, on the right by a vertical line. And also on the left hand side I have this region. Again, I can think of these two as separate functions, right? I can think of the blue curve above here as a separate function from this guy. Can you tell me what is this guy as a function of x? As a function of x, what is the blue curve between -3 and -1? Well, what was y? Remember, the y was y was 2x plus 6, right? Sorry, y squared was that. So what is y? Y would be positive root of that or negative root of that, right? If you take the positive root of 2x plus 6, you get the blue curve above. If you take the negative root of 2x plus 6, you get the part of the parabola below. So you can use that to see it as a type 1 region. So you can find the area on the left of -1 by using type 1 region, area on the right of -1 as a type 1 region. Use the formula for type 1. You can do this problem that way, but the difficulty is you have to compute two integrals. Not only that, now you have to deal with root functions, right? Because of what? Because the functions are now root functions, right? Am I making sense? So it turns out doing it that way is more difficult, obviously, and so that's why we need to know both types of regions. Okay, how to deal with both types. All right, everybody is okay with this example. Done with 5.1. All right, now I want to speak about computing volumes. That's the topic in section 5.2. Okay, so what's the before I begin, let me recall some things. What is a right cylinder? A right cylinder means a region like this. A right cylinder means a solid where the top and the bottom, they are parallel and they are congruent. They are exactly this, geometrically they are the same. Like congruent triangles, congruent rectangles, right? So the top and the bottom, they are the same. They are congruent and parallel. And so this is that's what we mean by a right cylinder. Okay, you can think of the cylinder consisting of vertical line segments joining the top and the bottom. Vertical line segments joining the top and the bottom. Everybody's okay? Now, what would be the volume of a right cylinder? The volume of a right cylinder is the area of the bottom multiplied by the height. So here in the volume formula, H represents the height of the cylinder, A represents the area of the bottom, or you could say area of the top. They have the same areas. Usually what you deal with what? Right circular cylinder. What is a right circular cylinder? Well, right circular cylinder is a special type of right cylinder, and which is this, right? The top is a circle, the bottom is a circle, right? Everybody's okay? Now in this case, what's the volume of the cylinder? Area of the bottom multiplied by the height. Area of the bottom, because it's a circle, I can say it is pi r squared, right? That's the volume of a cylinder. Everybody's okay? Am I clear? Now I want to look at solids of revolution. Okay? When I say revolution, you should think of the word revolving. Revolve, not the political revolution or something. Okay? So solids of revolution. What is that? Imagine that I have a function f. Imagine that I have a continuous function f, and I have the graph of the function f over the interval from a to b. I have the graph of the function f over the interval from a to b. The graph of f is the magenta curve. The graph of f is the magenta curve. Everybody's clear? The graph of f is the magenta curve. Now look at the region between the graph of f and the x-axis. Look at the region between the graph of f and x-axis from a to b. Am I clear? Look at the region that I highlighted in magenta, right? The region between the graph of f and the x-axis from a to b. Now, think about this. I want to revolve that region around the x-axis. Revolve that region around the x-axis, and I'm going to end up with a solid, right? If I revolve the region around the x-axis, I'm going to end up with a solid, and that solid looks like what I drew there, with the limitation of my drawing skills. So we want to know the volume of that solid. One thing that I want you to realize here, look at the cross sections. What do I mean by cross sections? You have this solid. If I cut the solid with the vertical plane, right? If I look at the intersection of the solid with a vertical plane to the x-axis, vertical to the axis of revolution, then what do I get? What kind of region do I get when I cut it with the vertical plane? Well, I claim I should be getting a disk. No matter where I cut it, I should always get a disk. Why? Well, think about what you're doing. You have this region, right? This region is being revolved around the x-axis. So the way you are obtaining the solid is basically this. Look at each line segment. So take any x between a and b. Look at the line segment from the point x0 to the corresponding point on the graph, right? What is the height? What is the height of the red line segment? The height of the red line segment is f of x, right? Because that's the height of the graph at x. So what are you doing? Well, you are basically revolving the red line segment. You are revolving the red line segment around the x-axis, right? So every single line segment is being revolved around the x-axis. So when you revolve this line segment around the x-axis, you get a disk, right? Can you tell me what's the area of that disk? Pi r squared. What is r? Not x. F of x, right? F of x is the height, is the length of that line segment, right? So the area of that cross section is pi times f of x squared. And what is the volume? Well, the volume turns out to be the integral from a to b, of pi times f of x squared dx. So what am I doing? I'm basically integrating the cross-sectional area, right? I am integrating the cross-sectional area. So at any x between a and b, I have the cross-sectional area, and I have a single formula for all the cross-sectional areas, right? This integrand that I have it tells you the cross-sectional area at any x, right? So I'm integrating the cross-sectional area function in order to come up with the volume. So you can imagine that I am basically adding up the areas of all the cross-sections, and that should be the volume. And now I want to give you why this is the formula for the volume. I want to justify to you that that's the case. In order to justify that, let me make it look at a different picture. Because my other picture was so small that I couldn't work on it, I'm trying to make a big picture here. In this picture, the graph of the function f is this curve. So the graph of the function f is the curve, the black curve from A to B. And imagine the region below the graph of f, and you are revolving the region below the graph of f above the x-axis, around the x-axis, right? You obtain a solid like this, right? If I revolve the graph of f around the x-axis, while I'm revolving, it's important to realize I'm revolving not just the graph of, I'm revolving the region between the graph of f and the x-axis, from A to B around the x-axis, and I'm getting a solid like this. Everybody's clear? Now, how would you estimate the volume of this solid? If you were given a solid like this and you were asked, give me an approximation of the volume, what would you do? Well, one thing you could do is pick a big partition of the interval from A to B. Pick a large partition of the interval from A to B. Okay, let's think about n. So x1 to xn, that's the partition. x0, x1, x2, xn, that's the partition of the interval from A to B. N is big, a couple of trillion, whatever you want to imagine. And then what I'm going to do is I am going to cut the solid at x1, x2, all the way up to xn minus 1 by using vertical planes. By using a vertical plane, I am going to cut the solid at x1, x2, xn minus 1. Is everybody okay? I'm going to get small pieces, right? I'm going to get small pieces. How many small pieces am I getting? Well, as many As many subintervals I have, right? I took a partition for each subinterval. I have a small piece, right? For each subinterval, I have a small piece. How would you estimate the volume of each piece? That's the question. How would you estimate the volume of each piece? Okay? Well, I'm going to concentrate on the ith subinterval, and I'm going to look at this piece, yellow piece here, and I'm going to try to see how I should approximate the volume of that piece. Well, what I did here is that in the ith subinterval, I picked a number wi. That's the sample point, wi. And at wi, if I look at the cross section, right? If I look at the cross section at wi, I get a disk, right? What is the area of that disk? Well, depends on what's the radius of the disk. Well, what's the radius of the disk is basically the height of the graph of f at w, right? The height of the graph of f at wi, that's the radius of the cross section at wi, right? That is, if you revolve the line segment, the magenta line segment, right, around the x-axis, you get the disk. So this one has length f of wi. You agree with me on that? Now, would you agree that if my partition is huge, these pieces are so tiny that I can approximate this piece by assuming that this is just a cylinder. If it is very small, then the bottom is a disk, the top is a disk, right? I can assume that it's so tiny that they are about the same. So this is just a right circular cylinder. What's the volume of the right circular cylinder? So I can say this is the volume of the ayat piece. What is that? The area of the disc in the middle multiplied by the height of the cylinder. The height of the cylinder is equal to the length of the subinterval. Agree with that? So that's the volume of the ayat piece. So now sum up over all i's, right? For each subinterval I have a piece. I approximate in the same way. So if I look at the sum I going from 1 up to n of pi times f of wi squared delta xi, that's going to give me what? That's going to give me an approximation of the total volume. Well, guess what? This is the Riemann sum of what function? Remember you did some exercises where you were given a Riemann sum and you were asked to write down this is the Riemann sum of what function, or what integral does it represent, right? Well, as n goes to infinity, this guy is going where? As n goes to infinity, this guy is approaching to an integral from a to b of what function? Well, it is pi times f of x squared dx, right? So that's why that's the formula for the volume. Remember, that's what I said, that the volume of a solid of revolution like this, where I am revolving the region between the graph of f and x-axis from a to b around the x-axis, then the volume is given by this formula. Again, it's important to realize what you're doing is that you're integrating the cross-sectional area, right? The integrand here represents the area of the cross-section at x. The area of the cross-section at x. X is going from A to B. So you're summing up the areas of the cross-section, right? You're summing up the areas of the cross-sections, okay? And that's the volume. Is it clear? Should we do an example? Let's do an example. So let's say find the volume of the solid obtained by rotating about the x-axis the region under the curve y equals to root x, where x extends from 0 to 1. So what region are we talking about? Well, we are talking about the region below the graph of root x. The graph of root x is what? It's like upper half of the parabola y squared equals to x, right? So the blue curve is the graph of root x, and it extends from 0 to 1 only. And if I revolve the region below the graph of root x above x-axis, right? If I revolve the blue region around the x-axis, I get a solid which looks like what I drew there, okay? You guys see what the solid is, okay? And what would be the volume? What would be the volume of that solid? Let me erase this. Well, I guess you guys have seen it already, but let's try to do that again. What's the volume of this solid? So what should I do? Let me erase a couple of more things here. So what am I going to do in order to come up with the volume of this solid? Well, first of all, what I have to do is pick any x between 0 and 1. And once I pick any x between 0 and 1, I am going to look at the height of the curve at x. And I'm going to look at the line segment from at x, extending from the point x0 to the point on the graph. So can someone tell me what is the what is the length of this segment? The length of that segment, because it's the graph of the function root x, at x the height of the graph would be root x. Right? This point here has coordinates x and root x. Right? So for any x between 0 and 1, the height is root x. So basically then, what is the area of the cross section at x? So the integral would be from 0 to 1, and what do I have to integrate? I have to integrate the cross sectional area. What's the area of the cross section at x? Well, if you revolve the red segment around the x-axis, you get a disk of radius root x, right? So it will be pi times root x squared. That's all, and dx. Oh, darn, I forgot. What did I have as the final answer? Pi over 2, very good. So I had pi over 2. Again, computing the integral is not the main issue. The main issue is setting up the integral. And once I set up the integral, I'm done, okay? Pretty much. And in your exam, I will be asking you to set up the integral only. You don't have to evaluate the integral. I am going to stop here, but we still have a few more things that we have to finish. Maybe I'm going to use 20 minutes tomorrow to finish section 5.2, and this is it. Your final exam will be up to section 5.2.